types of radiation. The first one that we've got is the alpha radiation. So that uses the Greek letter alpha, looks like the Jesus fish, and that's the one that has a very high ionizing ability, so the ability to destroy the DNA, so it's very, very dangerous in that context, but it has very little energy and very little penetrating power. So you can stop it by a piece of paper, the surface of your skin, all of those things. So that's our alpha radiation. If we go back to the nuclear notation, and I start with this radioactive element, it's element X, it has Z protons, and A is its atomic mass, the protons plus the neutrons. If this thing then decayed into something else, we would call that thing Y. Nice and creative. I start with the element X, it decays, produces radiation, etc., into element Y. If I'm talking about the alpha radiation, it turns into Y, plus it also gives off alpha radiation. And alpha radiation is just a helium nucleus. So if I look at helium, helium has 2 protons. Helium has 2 protons, 2 neutrons, but it has no electrons. So this is just the nucleus part of a helium atom without the electrons. That's why we call it a helium nuclei. So this is produced, Y and an alpha. This is kind of like balancing a chemical equation that you've seen in chemistry previously. Remember, the conservation has to hold. So if I start with Z protons, this is going to have some amount, but I've lost 2 to the alpha particle. So therefore this has to be Z minus 2. And for the record, this is just the way that I often write the Z's with a line through it. I got it from the military and it's stuck, but if you don't like it, you don't have to write the Z. Just write a normal person Z. So, Z minus 2. This is happy. I've got 2 here. I've lost 2, and that gives me back whatever I started with. That's the Z. Now if I look at the A, I'm going to have whatever I started with, and I subtract whatever I've lost, which is 4. So this is the general equation for alpha decay. I start with something, splits into this smaller thing that's lost protons and neutrons, and it's produced alpha. So this is no longer X. That's the key here. Remember, in the previous example, I said that the protons never change. In this case, when we're talking about radiation, we are losing protons. So this is a completely different element to this. It's changing into another element. Now if we look at beta radiation or beta radiation, it uses this symbol, which is the Greek letter beta. And beta radiation is less ionizing than the alpha, but has a little bit more penetrating power. So it takes a thin sheet of metal or a few sheets of paper to stop it, whereas in the alpha radiation, it took very little to stop it, but it was a lot more ionizing. Important notation to start with, before we get into the actual general equation for beta radiation, these 2 things. So looking at the notation we've looked at before, we know this is the atomic number, and this is the atomic mass. So these things are going to look a little bit weird. Firstly, how can we have negative protons? And also, how can you have no protons plus no neutrons? It doesn't quite make sense. To fit the notation, we use this to say that in 0, it means the thing has no protons. It's not a nucleus, it's not actually an element. And the negative and the plus symbolizes its actual charge. So here we're not saying it has plus 1 proton and it's minus 1 proton. We're saying this is a positively charged thing with no protons, no neutrons. This is a negatively charged thing with no protons, no neutrons. So in this case, when we talk about these 2 things and when we see these 2 things, what do we know that makes up part of an atom that has no protons, no neutrons, and has a negative charge? And ironically, the letter gives it away. It has the symbol E. So this is an electron. So in beta radiation, the radiation that's actually given off is a very high energy electron. In alpha, it was spitting out a helium nucleus, a very tight small ball of protons and neutrons. In beta, it's firing out a super high energy charged electron. So what would this be then? This is an E. It has no protons and no neutrons, so it's suggesting that it's an electron, but it's positive. So scientists are really good at being creative when they name things. What would you call something that's an electron that's positively charged? A positive electron? Almost. In this case, we call it a positron. An electron that is positive. So that's all it is. It's a positively charged electron. So when we talk about beta, we're going to have beta plus and we're going to have beta minus. There's two types of beta radiation that we can get now. This is all to do with whether we produce an electron or whether we produce a positron. So positron, beta plus, electron, beta minus. Firstly, with beta plus radiation, it's important to know that if we start with a proton, and a proton is going to look like a 1 and a 1. It has one proton and it has no neutrons, so just 1, 1. In beta plus decay, a proton splits into a neutron plus a positron. So a neutron has no protons. So it has a 0 atomic number, but it is a neutron, so it has a 1 up here for its mass number. And then I've got my 1 here in my positron. So this here is balanced out by my positron's atomic number. So even though we're talking about this is basically a high energy electron, the mass or the atomic number is conserved here. This has got a 0, it has no neutrons. This has 1 neutron, this has 1 neutron. So neutrons are balanced, proton's atomic number is balanced. So this is beta plus. We don't actually split the element into by another element by taking away neutrons. What actually happens is one of the protons decays into a neutron plus a positron. So that's your beta plus radiation. Let's take a general example. If I had element X and we're saying that it's going to decay through the beta plus option, it is then going to decay into some element Y, but beta plus is going to produce a positron, so this is going to be a +1, 0. And then in beta plus, it also produces this thing. Often you won't see the E, that's just a bit of a notation, so you can ignore the E and it's just kind of like a cursive V. And this thing is called a neutrino. It has no protons, no neutrons. It's a subatomic particle. We'll talk about that later on in the chapter when we get into some of these subatomic particles, so neutrinos and other things. So this is your beta plus general equation. Decays into a Y, we've got the positron plus the neutrino. You can see that neutrino has no protons, no neutrons, so it doesn't affect the balance whatsoever here. However, our positron has a +1, it's gained or taken away a proton, we can think of it that way. No neutrons though, hasn't affected that. So this A, protons plus neutrons, has to just be A. That hasn't changed, that balance is still the same. However, if we look at the Z, if I've got a +1 here, I've gained 1 from my Z, that means this has to have lost the 1 to balance out. Now I can check. Z minus 1, +1 minus 1 gives me the Z. A goes to A, 0, 0. Everything is balanced. So this is your beta plus general equation. So as long as you've got your positron and the neutrino doesn't contribute to this situation. So if you forget to put it in or you leave it out, whatever, it doesn't affect the general equation. But in this case, neutrinos are produced. Beta plus radiation, it works a little bit different. In this case, it's going the other way. We've actually got a neutron that decays into a proton. So it becomes a proton. So I start here with my neutron. It now will decay into a proton. And we know that a proton is going to be 1, 1. And then in beta minus, we're also going to have that negative thing that we expect, which is our electron, a high energy electron. And then, just to throw a third spanner in the works, beta minus, whereas in beta plus we saw that it produced that neutrino, in beta minus we produce this thing, which is an anti-neutrino. So the easiest way to remember is you've got the line. Think of the line as like crossing it out. So if you ever cross something out, you're saying no to it, no smoking, no swimming, whatever those signs say. The line is a no. So an anti, and this V, the cursive V, just like we say with velocity symbol, this is your anti-neutrino. So beta minus, your neutron decays into the proton. It also produces the electron, and it gives off this seemingly useless antineutrino. So let's look at the general equation now. General equation for a beta minus radiation. We're going to start off with our X. Element X, the mystery element. This will decay, as usual, through beta minus. So as soon as we see the beta minus, we know that the electron's going to be produced. The beta radiation always produces an electron, but whether it's an electron or a positron, the negative and the plus will tell you that bit. We also know that it's going to produce this mysterious, seemingly useless antineutrino. The neutrino with the anti line on top. So therefore, what has to be left? What's the thing in front of it? Well, that's whatever the element has become. We started with an element. X has turned into Y. We've also produced this electron and this antineutrino. Now we just need to go along and balance. So in this case, we've got a -1. So if we've got a -1 here, how do I balance this? It would have to be a Z plus 1, right? It's seemingly gained a proton, which is what we expect, because in beta minus, the neutron decays into a proton, so it can gain the proton because the neutron has given it to it. So we've got a Z plus, and we can check by saying the Z minus, -1 plus 1 gives you 0, Z, Z, everything's balanced. Now if we look at the top, we've got A, so our atomic mass, our protons and neutrons, we started at A. I've got a 0, I've got a 0, so I haven't added or subtracted anything from here. This has to then be A. So it's unaffected. All we've done is we've added one here. These are balanced out. That is the general equation for your beta minus radiation. The third and final type of radiation is gamma radiation. Often the most commonly known, both by comic series such as the Hulk, and also just it's the most notorious for being the damaging or the unstoppable radiation. Gamma doesn't have the ionizing that alpha and beta have, but it's also got a very high penetrating power. It takes a lot to stop gamma radiation. We need thick lead or very, very thick concrete, those kinds of things. So gamma rays, we use the symbol gamma, the Greek letter. It looks kind of like, you can write it as either a bit of a Jesus fish, or often they'll just write it as a bit of a cursive Y shape. Either is fine. So, in gamma radiation, what happens is that after the alpha and beta radiation have occurred, there's excess energy left over within the system. And that energy is produced as high energy electromagnetic radiation, which is your gamma. So it's just very, very high energy. That's all it is. It's not a nucleus. It's not an electron. It's pure energy. Because of the fact that it's energy, it has a 0, 0, which means it's virtually high energy light. And as a result of it being light, it moves at the speed of light. So gamma radiation travels as fast as the speed of light. It's very, very quick. If we look at a reaction or an equation, I start with my mystery element X. It will then decay into what? If the only thing that's produced is gamma in this case, which is a 0, 0, that tells me that the thing produced is just whatever I started with. So my X becomes or stays as XAZ, but it produces this super high energy from the excess energy of the system, speed of light gamma ray. So that is my gamma radiation. This one's nice and simple. Doesn't change the element. The element is not decaying into another element. It's just emitting huge amounts of energy in this form of gamma radiation. Let's look at an example of this. So if I started with the element iodine, its atomic number is 53, and its atomic mass is 131. Iodine is radioactive. So when iodine decays or breaks down, iodine decays into the element xenon. Xenon has the atomic number 54. And in this case, it has 131 protons and neutrons, its atomic mass. So I could look at this and I could figure out what kind of radiation are we talking about here. I've gained a proton virtually from nothing. So we think about, what do we know that produces that? That's a beta radiation. So that means if it's a beta radiation where I've gained a proton through decay, that means if I've gained one, I need to minus one. And this would be my electron. This is my high energy electron. So far this is just a beta radiation, except in this case, when iodine decays into xenon and produces this beta radiation electron, it also produces our gamma 00. So this is our gamma radiation that's produced as a byproduct or at the same time as the iodine's beta minus decay. So this is an example of how it works in the real world. It's not just iodine just suddenly gives off gamma and remains iodine. It's a byproduct of excess energy within a system as it decays. So this is an example of something that happens all the time and produces gamma radiation.